Oscillations are a phenomenon that we encounter again and again in nature. From something as simple as a child swinging on a swing to something as complex as an aircraft wing bouncing around in turbulence, oscillations always occur when there are at least two entities or two agencies within a system which are storing energy and trading energy with each other. For example, consider the swinging pendulum. So here we have a pendulum and it has been disturbed from its mean position. So it is swinging in an arc again and again and again. The initial impetus or impulse given to the pendulum has given the bob kinetic energy, and as it changes its height above the ground, it gains or loses potential energy. So we are seeing a trade between the kinetic energy of this object and the potential energy due to gravity. Two different sources of energy which are trading energy amongst each other. It turns out that oscillations of all types follow this general pattern. We have at least two places where energy is being stored in the system, and this energy is being transferred from one source to the other or from one storage medium to the other. Consider the example of a circuit which contains a capacitor and an inductor. So we have two different components, both of which are capable of storing energy. Note that we are not considering any resistance in this circuit, as a resistor cannot store energy. A resistor can only dissipate electrical energy. So we start out with some charge Q existing on this capacitor, but at time t equal to 0, when we start the experiment, we have just closed the switch which completes the circuit between the capacitor and the inductor. Now, the inductor has no charge on it, it has no current through it at this time. So, the capacitor begins to discharge, and as a result, a current I will begin to flow. In response to this current I, the inductor L will start developing a magnetic field, and due to its self-inductance, it will start generating a back EMF. We know that the sum of all the voltages inside a closed loop has to be 0 by Kirchhoff's law, and this allows us to construct our first equation. So we can say that Q upon C minus L di by dt is equal to 0. Here Q is the total charge stored on the capacitor when we began the experiment. Capital C is the capacitance, L is the self-inductance of the inductor, and di by dt is the variation of the current in the inductor at that time, and the sum of these two potentials will be equal to 0. Note the negative sign on the inductor voltage here. That tells us that this voltage induced in the inductor is opposing the change caused by the discharging current of the capacitor. We can express a current I in terms of the negative rate of change of charge in a given region. If we use this information here, we can say that Q upon C minus L di by dt equal to 0 can be rewritten as d2q by dt square plus 1 upon LCQ is equal to 0. If you think about what we had learned about simple harmonic motion in class 11, you will notice that this equation is very similar to another equation that we had studied, which is d2x by dt square plus omega naught square x is equal to 0. So we can say that both of these are examples of simple harmonic motion. And in this case, we can say that omega naught, which is the characteristic frequency at which the system is oscillating, can be given as omega naught is equal to 1 upon root LC. And we can also say that the charge being developed or the variation of charge with time is given as Q is equal to Qm cos omega naught t plus phi, where omega naught again is the characteristic frequency of the system and phi is the phase angle or the phase difference between the variation of charges. Now, when we just begin the experiment, as I said before, there is no back EMF in the inductor, there is no charge or current flowing through the inductor. So we can say that at this time, phi is equal to 0. There is no phase difference. So this tells us that Q is equal to Qm cos omega naught t. We do not have to consider phi in this case because there is no phase difference at this time. And we can say that Im is equal to omega naught Qm, where Qm is the maximum charge attained in the capacitor at any given time, and Im is the maximum current in the circuit at that time. In this system, we notice that there is an interchange of charges and as a result energy between the capacitor and the inductor. Let's visualize how this works. So let's start with the capacitor. Which has some charge existing on it at t equal to 0. That is when we begin the experiment. And as soon as we complete the circuit and connect the capacitor to the inductor, the capacitor begins to discharge due to a current I, which is traveling in this circuit. Now, as a result of the current starting to flow through the inductor will start developing its own magnetic field in response to this current. So here the inductor will start developing its own magnetic field, and as a result of this there will be a self-inductance in this inductor which will cause a back EMF to start developing, which will depend on the inductance and the rate of change of current in this circuit. This process will go on for some time until the maximum value of current is reached, the maximum magnetic field is reached, and then the direction of current will reverse itself. So what will happen now is that the capacitor will start being charged by the back EMF coming from the inductor, and the charge will accumulate in the opposite polarity and the direction of current will reverse itself. As a result of this, we notice that the charge in the system is getting transferred between the capacitor and the inductor and back again and again. The polarity of the voltage on the capacitor will keep on changing and reversing itself. This is very similar to what happens when you have a spring mass system, where if you give a momentary disturbance to this mass, the mass starts oscillating back and forth, and if there is no friction in the system, this oscillation will keep on taking place forever. So we notice that there is an analogy between the phenomenon that we are observing in this electrical network and the phenomenon that we observe in mechanical systems. And this is not an accident. Since both of these systems can be described by the same type of differential equation, we can find analogous quantities between these two experiments. For example, we can show that there is an analogy between mass m and the inductance L of the system. Both represent inertia and unwillingness to change their current state. Mass tries to remain stationary or keep moving at uniform speed. In the same way, an inductor will try to maintain constant current through it. Spring constant, which is denoted by K in mechanical systems, has the analog of the inverse of capacitance in electrical systems. Displacement, denoted by X in a mechanical system, has the analog of charge in the electrical system. Velocity is the time rate of change of displacement, or the differentiation of displacement with respect to time. So that can be defined in the terms of current in an electrical system, and the total energy of the system in the mechanical case is the potential energy plus kinetic energy, that is half kx square plus half mv square. When we come to the electrical system, where we have a capacitance and an inductor, we have the total energy as being half q square by c plus half li square, the energy stored in the capacitor and the inductor at any given time. In fact, this analogy between mechanical and electrical systems is so close that we can actually use it as a low-cost method of analyzing mechanical oscillations, where an actual experiment would be too expensive or difficult to arrange. For example, if we want to analyze the behavior of the shock-absorbing system on a suspension in a car or a bike, we can create the electrical analog of that system for a very low cost and simulate the behavior of the system under various conditions. So this gives us a very novel way of analyzing mechanical systems using electrical analogs.
Manorama Horizon. Learning made simple.